a competition from a high school competition or contest back in the United States back in 2016. Fairly certain this was in San Diego, California. Okay, now what we're given is a polynomial, quadratic polynomial. We're supposed to find all primes p and q such that g of p is equal to g of q plus 678. They had another constant, I think, on this particular problem. So this is just another problem, very same structure, except we have a different constant here. Now remember what a prime is. A prime is a number like, for example, 7. 7 is equal to 7 times 1, because a prime number is any number such that the prime factorization is just 1 in itself. Any other, like for example, 8 would be 2 times 4. That's a composite number, right? It's called a composite number. But notice that what I've done here is a little bit of algebra here. We did this right here because g at p minus g at q is actually equal to the constant 678. Okay. Now, as far as the algebra goes, it works out rather nicely. You end up with a very convenient difference of 2 squares. Now, I like to mention this. Practice competitors know this very well, but somebody just getting used to math might forget this 1 that's in front of the p minus q, right? The 1 that you see right here is exactly where this 1 came from. Now, the benefit of getting this factor this way is we can equate it to the divisor pairs, factor pairs of 678. Now, note that this isn't really that important to, well, I guess it is just for the sake of completion. Since you have 0 as a possibility for exponents to allow for 1 and 678 to be a divisor, we actually have 2 times 2 times 2 divisors. It's just a basic combinatorial argument. You actually have 8 divisors. Now, a lot of people just write down the 8 divisors, no problem, but this kind of is a terminate condition in case you think you may be leaving a divisor pair out. All right, so the very first divisor pair that I picked was just 2 times 339. That's 2, and then 3 times 13 is 339. Okay, now a very cool thing happens right here. Also, by the way, p minus q is definitely a smaller number, definitely smaller than the other factor, which is p plus q plus 1, right? Okay, and I guess that's important because if you look right here, what I did is I equated p minus q, the first factor, with 2, okay? Then I equated p plus q plus 1 with 339, the second factor. Now, a nice thing happens here. When you sum these two equations, the q's kind of self-eliminate. So this is a room service, made to order sort of thing. If you add these two things up, the q's cancel, and you end up with 2p plus 1 is equal to 441. But notice that leads to the absurdity p is equal to 220. And remember, p has to be prime, so we have to rule out this possibility. Okay, this leads to the condition that p would be an even number bigger than 2. 2 is the only even prime. And so this is an impossibility, if you will. So I'll just put a big old X next to that, okay? So we've done case 1, if you want to call it that, okay? Now we go down. This time we associate 2 and 3 to get 6 right here. And in a similar fashion, we carry on. The q's self-eliminate. And this leads to the result 2p equals to 118, which certainly implies that p is equal to 59. And which is a prime number. Doesn't require you have to check 7, 5, 3, and 2. Okay, the square root of 59, and then all the prime divisors less than that, right? All right, so p is equal to 59. And that would force q to be equal to 53 from this statement right over here. Now the question was to find all such primes p and q that satisfy these conditions. Well, so far we've found 2. Q equals 53. P is equal to 59. Okay. Again, we were looking for, this should be all primes, right? This should be, oh, sorry about that. This should read all primes. Let me go ahead. I need to correct that for the thumbnail. That should be all primes. All right. So we have found a pair of primes. Okay, we found a pair of primes. Now, again, if you do the same thing for 3 times 226, which is another possibility, right? And that happens when you pair up 2 times 113 is 226, right? So that's where we get this right here, okay? And then again, when you do this, you would get 2p is equal to 115, which is certainly an absurd condition since we're living in the world of integers. It's a number theoretic problem. So you get 2p is equal to 115, and we'll put a big fat X next to that also. So this is impossible. Now, y'all, I did leave out, I just realized I left out 1 and 678, but it's very clear that doesn't work. You guys can verify that. But 1 times 678 also leads to some sort of absurdity. And I'll go ahead and stop right now, but that's also an impossible condition. So we've quote checked all 8 of the divisors which come in pairs. And our conclusion is that Q equals 53 and P is equal to 59 are the only 2 primes that satisfy this condition. So we'll write down P, write it down up here. P equals to 59. Okay, and then Q equals to 53. Okay. Good night.